Hello everyone, this is Dr. Daya Sagar Chowdary, Senapati, Assistant Professor, Department of Electronics and Communication Engineering, Aditya University. So today our topic is conversion from one radix to another radix. So what is radix here? So previously we discussed about the base. So base is nothing but the radix. Also we can call base as a radix. So both are equal. And finally the learning outcome is convert the numbers between different radix systems. So not only these 4 radix systems, also the radix are 5, 7, already we observed the 9, these are also same. If it is 9, 9 to the power of 0, 9 to the power of 1, 9 to the power of 2, here also 9 to the power of minus 1, 9 to the power of minus 2. Likewise, if it is 5, 5 power 0, 5 power 1, 5 power 2, 5 power minus 1, 5 power minus 2. If it is 7, 7 to the power of 0, 7 power 1, 7 power 2, 7 power minus 1, 7 power minus 2. Likewise, we have to represent for any number system conversion. So, we already discussed about these number systems. So, we know about the decimal, binary, octal, hexadecimal. We already discussed about all these number systems. So, we know from 0 to 9 and 0 1 and 0 to 7 and 0 to 16. So 16 means here 0 to 15, that is 0 to F representation in hexadecimal. Now the basic decimal number system we have to represent here. So here decimal number system representation. So base 10, this is the base 10 representation. How we can represent a decimal in a decimal. So here this is the decimal actually we have taken here. So this is the base 10. So base 10 or radix 10 here. So depending on the position of the symbol, the total number is varied. So that means 6. So 6 is in units place. That is why 6 into the base is 10. So 10 to the power of 0 and plus 8. 8 is in tens position into 10 to the power of 1. So 10 is the base. That is why we simply multiply with the 10 to the powers, and 5 is in 100 position. So 5 into 10 to the power of 2, this is the hundreds position, and 2 is in thousands position, that is 10 to the power of 3. So that means 2 into 10 cube, which is nothing but 1000. So 2 into 1000 is 2000 plus 5 into 10 square, which is 500 plus 8 into 10 to the power of 1, that is 80 plus 6 into 10 to the power of 0. So 10 to the power of 0 is 1. So 1's position, 6 into 1 is 6. So likewise, this is a simple decimal number system representation. Likewise, we represent the number system. So that is 2, 5, 8, 6 and the radix is 10. This is the number system representation. That means we are taking the decimal number system. This we are expanding the numbers, their number. Now, this is a decimal to binary number system conversion. So now we know previously we discussed about 0, 1, 2, 3, 4 so on up to infinity. We can represent the binary like this. Now how we can calculate for any number to binary? So let us come to the point. So take the example as 35. So 35 is in decimal. So 35 is in decimal. Now which we have to convert it into. Convert it into means this is the question mark. We have to convert it into binary. So binary base or radix is 2. Here this is decimal, that is radix is 10. Now we are converting radix 10 to radix 2. Now 35. So here the input is 35. So 35. So we have to take the LCM with the help of 2. So 2 17s, 34 and 1 is the remainder here, and 2 again we have to take the LCM for 17 with the 2. So 2 8s are 16 and 1 is the remainder here. Always we have to use this remainder small dash, and that remainder we have to use for each and every result. So 2 4s are 8, so remainder is 0, and 2 2s are 4 and the remainder is 0. 2 1s are 2 and the remainder is 0. So now we have to take the result from bottom to top. That means 1, this is the 1 representation, next 0, this is the 0, next this 0 is 0, and this 0 is this one, and 1 is this one, and this final one is this one. So this is the final representation 0 0 1 0 0 0 1 1. So this is the binary representation when we have given the decimal 35 in decimal number system 35. So this is the simple conversion from decimal to binary number system. Before going to binary number system, we have to observe or identify the two positions of the binary. So mostly we discuss about LSB and MSB. So LSB is nothing but least significant bit. Most significant bit is the MSB. That means rightmost position we call this one as a LSB, and leftmost position we call this one as a MSB. So before and all there is no representation, but if we want to, this one's position means we can represent like, so second position from the MSB. If we want to represent this position means third position from the MSB, or if we want to represent this position means second position from the LSB. So likewise we will represent the binary number system. Now, so binary to decimal again. So now previously decimal to binary we have already calculated by taking the LCM with the help of 2. Now binary to decimal number system, how we calculate, let us see. So I have taken one example, 1 0 1 0 1 is the binary number system. Simply it is represented in 2 as a radix. So now, so we have to, radix is 2. Now we have to calculate this first one is this one into 2 to the power of 4 and plus 0 into 2 to the power of 3, this 0, and 1 into 2 to the power of 2, that is 1, this one, and this 0 into 2 to the power of 1, this 1, this 0, and 1 into 2 to the power of 0, so this one. So that means, so from right side to left side we have to calculate actually. So 2 to the power of 0, this is the units position, that means we call this one as a LSB. So 2 to the power of 0, and that means 1 into 2 to the power of 0, and the next position 0 into 2 to the power of 1, and the next position 1 into 2 to the power of 2, next position 0 into 2 to the power of 3, and 1 into 2 to the power of 4. This is the representation, first step. Next, 1 into 2 to the power of is 2 to the power of 4 is 16, and 0 into 2 to the power of 3 is 0. Anything which is multiplied with 0 is 0. And 1 into 2 to the power of 2 is 4, and 0 into 2 to the power of 1 is, again this is 0, and 1 into 2 to the power of 0 is 1. So now these three are the values. So total is 21, base is 10. That is simple conversion from binary to decimal. Now decimal to octal number system. So this is the decimal to octal number system. We have already given the table here, that is why we kept the table here. Now we have to calculate the decimal to octal number system other than this table. Okay. Now I have taken 88 as an example here. So 88 which is in decimal, that is 10. Now we have to convert it into octal. So this is the octal. So radix is 8. That means radix 10 to radix 8. This is the representation, conversion of this number 88 to from radix 10 to radix 8. Now how we can calculate? As usual, already we have done this thing in the binary, the decimal to binary concept. Simply we have to take the LCM with 2. Now here we have to take the LCM with 8. So 8, so 8 is again 88, for we have to take LCM. So 8 11 times 88, and so there is a 3, so 8 11 say 88, so there is a the remainder is 0, 8 ones are 8, so 8, so and 11 minus 8 is 3, so the remainder is 3, and 8 zeros are 0, and the remainder is 1. So from bottom to top, so 1 3 0. So this is the representation of octal representation from decimal. So here this is a simple representation. So no need to calculate from this one is decimal to octal. So octal is, this is the base and this is the octal. So 10 to 8, there is no difference in this. Now octal to decimal. So octal number system to decimal number system, again we have take because the radix is 8 here. So now 2 into not 2, because here we have to take again the LSB. So 7 multiplied 8 to the power of 0. So this is radix is 8. So that is why 8 to the power of 0 plus 5 multiplied 8 to the power of 1 plus 0 multiplied 8 to the power of 2. 2 multiplied 8 cube. So the simplification is 1024, which is nothing but 2 into 8 cube, that is 512 into 2, that is 1024, and this one is 0, the product with 0 is 0, and 5 into 8 to the power of 1, that is 40, and 7 into 8 to the power of 0, 7 into 1, that is 7. So finally 1071 base 10. So this is a simple conversion from octal to decimal. Now decimal to hexadecimal. So decimal to hexadecimal, how we can calculate? So again the same conversion. So with the help of 16 we have to take the LCM. So from 16, so 9, 10 is the example I have taken. Now 16 with 16, 56 times we will get the result as, and remainder is E here, and 16 threes are some 56, some remainder. So again 8 is the remainder, and 16 zeros are 0, and 3 is the remainder here. So from bottom to top, 3, 8 and E. E means here the representation E, we already represented E as here, but the maximum number is 14. So this is the 14 representation, 14 is the remainder here. So for 14 we simply replace the 14 with E, because there is no 14 in the hexadecimal. That is why 3, 8, E is the representation in hexadecimal. So which is nothing but 9, 10 in decimal. This is the simple conversion from decimal to hexadecimal. Now hexadecimal to decimal, again we have to convert vice versa, reverse. So this is the number I have given, 1AF. So 1AF, which is nothing but, which is in hexadecimal. Now this is the LSB. So F into 16 to the power of 0, because this is the power 0. So 16 power 0, and A into 16 power 1, and 1 into 16 square. So 1 into 16 square is 1 into 256, plus 10 into A representation is 10. So 10 into 16 power 1 is 16, and F is 15. So into 16 power 0 is 1. So 256 plus 160 plus 15. So this is the final decimal representation. 431 is the decimal representation. Not only the positive numbers, we have to represent the fraction number systems also in other number systems. That means here decimal number system fraction representation. So let us see how we can calculate. So so we know already, so this position is units position, this position is tens position, this position is hundreds position. After this point, this is the 1/10ths position, this point is 1/100ths position, this position is 1/1000ths position. So 10 times greater, this side 10 times smaller. So likewise we have to represent. Now this is a simple representation. Again we have to know. So 4 is 4 into 1, 3 is 3 into 10, 2 is 2 into 100, 1 is 1 into 1000. And after point, so right side of the point, 5 is 5 into 0.1, 6 is 6 into 0.01, and 7 is 0.001. So this is the simple representation of the fraction numbers. Now this is a simple conversion from decimal to binary fraction number system, fractions, for fractions. This is a decimal fraction. So I have taken one decimal fraction. So now we have to convert it into binary number system. So binary number system means, so we can calculate in a way such that first of all 10 we can calculate easily. Already we know how to calculate. But coming to the fraction point is here 0.625 is the fraction. So now left side we already taken the LCM. Now for right side we have to multiply with the fraction part. So with 2, because base is binary is 2. Now 0.625 multiplied with 2, which is nothing but 1.250. Now whatever we are getting left side of the point, we have to remove that one. So that means here 1.250. So subtract this one. So remove this one and place the 1 is here, because the 1 is your result. Now after 1 is removing, 0.250 is the again your result. Now 2 into 0.250. Now 0.5 is the, we are getting 0.50. Now 0.50, there is no value in front of this point, again we are taking 0 as a number. And 0.5 multiplied, again we have take 0.5 into 2, so 1, again 1 minus 1 is 0, so no need to calculate the beyond this one. So finally, previously we have taken the result from bottom to top for normal positive values, but here from top to bottom we have to take. So finally for 10 is 1010 is the binary, and for 0.625 0.101 is the binary. So this is the representation of the conversion of the decimal fraction to binary number. Likewise, this is also other binary number. Here 21.1 we are converting this decimal to binary. So 21 we can solve as usual. So binary by taking LCM with 2. Now we have to product the 0.1 with 2, multiply 2 with 0.1, so 0.2, 0 is the result, and 0.2 with 2, 0.4 we will get, so 0 again, so 0.4 with 2, 0.8, 0 again, 0.8 with 2, 1.6, so 1 we removed here, and 0.6 is there, 0.6 into 2, 1.2, so 1 is again removed here, 0.2. If we verified this 0.2 is 0.2, this 0.4 is 0.4, this 0.8 is 0.8, and 0.6 is 0.6. That means the result is also simply repeating. That is why the result is repeating means we can simply use this as bar if the result is repeating. Now binary fraction to decimal number system. So left side we are following 2 to the power of 0 multiplied, 2 to the power of 1 multiplied, 2 to the power of 2 multiplied, likewise we followed. Now coming to right side, so 0, 1, 2, likewise we are using the positive. Now for right side, take the 2 to the power of minus 1, 2 to the power of minus 2, 2 to the power of minus 3, something plus, something plus. So likewise we have to follow here. So after 0, this is the binary value, binary number I have taken 0.1101. So now this one, this is the one multiplied with 2 to the power of 1. So this is the 2 to the power of 1, plus this one is multiplied with the 2 to the power of minus 2, 2 to the power of minus 1, 2 to the power of minus 2. This 0 is multiplied with the 2 to the power of minus 3. So likewise we have to follow here. So again I have taken one more example 11011. So this one is multiplied with 2 to the power of minus 1. This one is multiplied with 2 to the power of minus 2. This 0 is multiplied with 2 to the power of minus 3. This one is multiplied with 2 to the power of minus 4. And the last one is multiplied with 2 to the power of minus 5. So no doubt here we are getting the fractional values only. So 2 to the power of minus 1 can be represented by 1 by 2, this is 1 by 2, 2 to the power of minus 2 is 1 by 4, and 2 to the power of minus 3 is 1 by 8, here 0 is multiplied, likewise 1 by 16, 1 by 32. So final, the result are like this, and finally if we sum up all these values, we will get this value which is in base 10. That means binary fraction to decimal number system. This is the representation, conversion. So here these are the some problems for practice. So we can solve this one. This is also a fraction from binary to decimal. This is a decimal to binary and hexadecimal, and this is in hexadecimal. conversion from hexadecimal to decimal. Here this is in octal to binary number system, and this is a binary number system to octal. So we have to solve these problems for practice. Coming to the summary, conversion between number systems involves changing a number from one base to other base using systematic methods. So here we are converting from one base to other base. So we already seen that from binary to octal, binary to hexadecimal, and octal to binary, and hexadecimal to binary. So common techniques include division, remainder method for integer conversion. So like LCM we are taking here, multiplication method for fractional conversion, and direct grouping for binary, octal, hexadecimal conversions. Radix conversion is essential for data interpretation, arithmetic operations, and interfacing in digital systems. Thank you.